So we've now seen an application of vectors and how we can do different things with vectors. It turns out there's a very clear connection between vectors and systems of linear equations. So every system of linear equations can be converted or represented as a vector equation. And similarly, every vector equation can be represented as a system of linear equations. So it transfers both ways. And anything that you can represent your equations you can solve by creating an augmented matrix and performing the reduced row echelon form on it. So let's just look at an example of converting between the two forms and how we would go about doing this. So here I have a system of two equations in two variables, and the first thing that I'll do to get this into a vector equation is I will actually break this up into three vectors. One which will pertain to the components involving x, one with components involving y, and then one involving the constants. So here I already see I have 3x and 1x. So I'm going to write 3x and 1x as a distinct vector here. And to that I am going to add the vector 2y negative 1y. And as we know about when we add vectors, we add straight across, we add the components. And so this still reads 3x plus 2y and 1x minus 1y. However, it's really just one expression instead of being two separate ones because it's one vector expression, even though it's two separate expressions combined into that. And then lastly, I will also do the same thing with my constants on the right. Now, in order to get this into the proper vector form that we want, the reason we bundled the x's together is because now I can factor out, it's just a scalar, it's just a multiplier on the components 3, 1, and here y is a multiplier on the components 2, negative 1, and that leads to the constants 22 and 4. So this right here is my vector equation representation. This is a vector equation. Probably guess it has an equal sign in it and it involves a comparison of vectors. So it's only one equation, which is interesting, right? This was two equations. This is a system of linear equations, and we were able to convert that into one equation, which is a vector equation. That's very handy. It's one equation instead of two. Okay, well, as you can see, we can go backwards too, right? If I had given you this x times 3, 1 plus y times the vector 2, negative 1 equals 22, 4, you could just bounce back in reverse order to achieve the system of linear equations. So if it's possible to get from a system to a vector, then it's possible to get from a vector to a system. Now, why do we study this? We do this for a couple of reasons. Sometimes it just makes more sense when you're modeling, when you're doing something in the real world to write a vector equation. It's more natural, but ultimately you're going to write an augmented matrix to solve it for you. So it's just kind of hard to solve, right? Because what we are asking here, and this is somewhat of a foreshadowing into when we talk about linear combinations, is I am asking essentially the question as follows. If I were to take the vector 3, 1, looks roughly like that, right? 3, 1, and I were to scale it by some factor. Well, remember what scaling does is it either makes it longer, it makes it shorter, or it even can reverse the direction. So essentially, by multiplying 3, 1 by x, I can move anywhere along the line that has a slope, a rise to run of 1 to 3. Now, if I do that same thing for 2, negative 1, here I'm going to take the vector 2, negative 1, and I'm going to scale it by a factor of y. And when I do that, and I put these, remember this means put them together tip to tail, I want to arrive here. I want to arrive at the point 22, 4. Now the point 22, 4 is just as a 2, 3, 4. It's going to be somewhere way out here, right? Somewhere way out here. I'm not going to draw this very accurately, but how would I essentially be able to take the 3, 1 vector, scale negative 1 vector? Well, you can imagine that I'd probably have to scale this thing up a bit, and then maybe that would land me here. This whole vector that I'm representing is x multiples of the 3, 1 vector. Could be fractional, could be decimal, could be a whole number. Notice that this one goes over 2 and down 1. So if I were to strategically find this value of x so that now if I went over 2 and down 1, there's my representation of just the 2, -1 vector, and then I scaled that by a factor of y. Okay, and since I'm putting these together tip to tail, remember that means adding the 2 vectors, and where I want to land, my finisher, is right over here at the point 22, 4. Now, writing a point as a vector and a vector as a point is kind of the same thing. It's still referencing the same geometric location, but often you'd write it as 22, 4. But since here it's a vector, we'll write it as the vector 22, 4. And so that's what I'm essentially asking when I'm writing this in vector form. Notice that this didn't involve 2 lines, 3x plus 2y equals 22, and x minus y equals 4. I never actually plotted those 2 lines. What I did is I asked the question of what multiple of the 3, 1 vector, tip to tailed with y multiples of the 2, -1 vector, will land me at the location 22, 4. Now that's kind of a harder question to answer, right? We can kind of guess at these, but ultimately we would take this guy here, the system of linear equations, and we would right, just graph that, and we would figure out, well, where do those 2 lines intersect? This is the system of linear equations viewpoint of what we're doing in geometry, and this is the vector equation viewpoint of what we're trying to do geometrically. Let's take a look at an example where it makes a lot of sense to just write a vector equation. A warehouse offers a box of 100 forks and 200 napkins, or a box of 50 forks and 50 napkins. Well, already we can kind of see that maybe we can represent the 2 boxes. I'll write them as box 1 and box 2. It seems natural that box 1 we could write as 100 forks and 200 napkins, and then the second one we could write as 50 forks and 50 napkins. And we need 400 forks and 700 napkins. So our need is 400 forks and 700 napkins. And what I can do is I can buy multiples of these boxes. So I can buy 1 or 2 or 3 or however many I want of box 1, and I can buy however many I want of box 2, but when I add those together I should get 400 and 700. So what we need here is we need some sort of variable. What's our unknown? Well, unknowns in this context would be the quantities of the boxes. So when we define our variables, we have to be very clear. We have to say the number of box 1, number of box 1s that we're going to buy, and y will be the number of box 2 that we're going to buy. We're never going to write this just as box 1 and box 2 because a variable is a measurement. A measurement has a unit. In this case, our units is the quantity of, right? It's not the size of or the volume of or the surface area of, it's the quantity of them. So every single box 1 will have 100 forks and 200 napkins. And if I multiply that by the number of boxes, that will tell me the total number of forks and napkins that I'll get just by buying X boxes of box 1. And then similarly, I'm going to buy Y multiples of 50/50. And well, what am I going to do with those 2? Well, I'm going to combine them, right? That's going to be the total number of, in the top row, forks and the total number of napkins in the bottom row. I need 400 forks and I need 700 napkins, and there we go. We naturally have a vector equation that was just real quick to put together. And now to actually answer the question of what should X and Y be, how many of each box should I buy? Well, now I could represent this as the system, 100X plus 50Y equals 400, 200X plus 50Y equals 700. And now furthermore, the way we often solve this is to put the coefficients of the same variable in the same column. The final column will always be the constants. Now you could see that you could go from a vector equation straight to the augmented matrix. Remember, augmented means to enlarge, and it's enlarged by the constants. That's why we call this the augmented matrix. And this is the system of linear equations right here. And now we can produce a reduced row echelon form, the reduction here. And so when we do this and using technology, we should get 1, 0, 3, and 0, 1, 2, I believe. Yes, that should work out. And so remember, our final step is always to figure out, well, what is this saying? It's saying 1x plus 0y equals 3. And 1x plus 0y equals 3 means x equals 3. 0x plus 1y equals 2, which means y equals 2. And so our solution set, which in this case is just a single ordered pair, is a unique solution, is x, y equals 3, 2. So we should purchase 3 of box 1 and 2 of box 2. We can verify that this all checks out, right? If I buy 3 of box 1, I'm going to get 300 forks. If I buy 2 of box 2, I'm going to get 100 forks. And 300 plus 100 is indeed 400. Also, if I buy 3 of box 1, I'll get 600 napkins. And 2 of box 2 will give me another 100 napkins. That's 700 napkins, and we've satisfied the conditions.